From one side of the world to the other, earthquakes appear to cluster along distant margins of the same restless planet. The question is not whether Earth moves, because it always does. The question is whether these far-separated ruptures are beginning to form a meaningful global pattern. This story follows the science, layer by layer. If this kind of calm documentary journey belongs here, please like the video, subscribe to the channel, and continue into the deep structure of the Earth. Earth presents a surface that appears calm when seen from far above. A blue and white sphere with broad oceans, long continents, deserts, forests, ice sheets, and mountain chains. Yet the solid ground is not equally still in all places. Over long records of observation, earthquakes gather in narrow belts and crowded arcs, while other regions remain comparatively quiet for years or even for centuries. The pattern first appears at the largest scale. Before any single fault or any single broken rock face comes into view, it appears as a map of uneven motion spread across the outer skin of the planet. On the surface, the most active regions form long curving zones that trace the margins of the Pacific Ocean. Around the western coasts of North and South America, across the Aleutian Arc, down through Japan, the Philippines, Indonesia, Papua New Guinea, Tonga, and New Zealand. Earthquakes occur again and again in numbers far greater than in most interior continental regions. This broad band is often called the Ring of Fire, though the name includes both earthquakes and volcanoes. In seismic terms, it marks a global concentration of repeated rupture, where the ground adjusts in frequent steps rather than resting in long uniform stillness. A second great zone extends from the Mediterranean region through Turkey, Iran, the Himalaya, and into parts of Southeast Asia. This belt is not as nearly continuous in shape as the Pacific margin, but it is still one of the clearest large patterns on Earth's surface. It crosses lands of high mountains, enclosed seas, dry plateaus, and crowded valleys. The earthquakes within it vary in depth and size, but together they show that active ground is not limited to the edges of the Great Ocean Basin. Motion also gathers across the linked lands between Europe and Asia, where crustal blocks shift, compress, and grind past one another over immense spans of time. Beyond these major belts, the ocean floor itself contains long lines of activity that do not often reach public attention. Many earthquakes happen far from cities, beneath open water, where no walls crack and no windows rattle for human observers. Instruments record them along submerged mountain chains and across remote parts of the seafloor. Their presence helps fill the global pattern. The planet does not shake only where people live. It shakes where the crust is under strain. Whether that strain is noticed by millions, by a ship at sea, or only by distant seismometers. When the full record is placed on a world map, each earthquake becomes a point, and the points together begin to resemble threads. Some threads are tightly packed and bright with repeated activity. Others are faint and broken. Large empty spaces remain between them. Much of Central Africa is quieter than the Western Pacific. Much of Australia experiences fewer earthquakes than Indonesia to its north. Eastern North America is quieter than the Pacific coast, though not free of seismic motion. Northern Europe is quieter than Turkey. The interiors of old continental regions often show far fewer events than active margins. The surface pattern is therefore not random. It is structured, clustered, and persistent. This structure becomes clearer when size is considered. Small earthquakes are very common. Moderate earthquakes are less common. Great earthquakes, the largest events Earth produces, are rare. Yet even these rare events are not distributed evenly. they tend to recur in the same broad surface belts that host many smaller quakes. The active regions produce earthquakes across a wide range of sizes, while quiet interiors usually produce fewer and generally smaller events, though exceptions occur. This unevenness matters because it tells scientists that the same regions that move often are also the regions most likely to release enormous stored strain. At the surface, earthquakes also show a relation to form. Deep ocean trenches, island chains, steep coastal mountains, and long linear valleys often coincide with high seismic activity. Wide stable plains and ancient shield regions often show less. The eye begins with geography, even before the deeper physical causes are explained. A narrow island arc in the Pacific, a mountain front in South America, a folded zone near the eastern Mediterranean, a fractured coast in Alaska. These surface forms belong to places where the ground has a long history of motion. The landscape itself does not create the earthquake, but it often reveals that the region has been shaped by repeated deformation. The apparent quiet of stable regions can also mislead. A quiet zone on the map is not a zone of absolute stillness. It is a zone of lower frequency. Earthquakes still occur within continental interiors, along old buried faults, near rifted margins, and in places with ancient scars in the crust. Some are large enough to damage towns and alter rivers. But when the whole globe is considered, these intraplate events remain scattered compared with the intense clustering along the major seismic belts. The difference is one of concentration, not of total absence or total presence. Observation over the last century and beyond strengthens this picture. Early global catalogues were incomplete, especially over oceans and in remote regions, because instruments were sparse. As seismic networks improve, the finer texture of the surface pattern becomes more visible. More small and moderate earthquakes are detected, and older assumptions become more precise. Yet the broad picture does not disappear with better measurement. It becomes sharper. The same regions continue to stand out. The same belts continue to dominate the global surface record. Improved data refine the map, but they do not erase its major structure. When people notice earthquakes occurring in different parts of the world within a similar period, the mind often looks for symmetry. It sees one event near one ocean margin, another on a far coast, another deep beneath an island arc, and begins to sense a larger arrangement, as if the planet is answering itself across wide distances. Sometimes these impressions reflect real clustering in highly active zones. Sometimes they arise from the ordinary behavior of a restless surface that always contains many active segments at once. Observations indicate that the Earth's surface does host regions of concentrated seismicity distributed across far separated belts. It remains uncertain, in any short interval, whether a visible grouping across opposite sides of the planet reflects a meaningful global pattern or a temporary arrangement within a constantly active system. At the outermost view, then, the first fact is simple and firm. Earthquakes do not cover the world evenly. They collect in belts, arcs, margins, and long broken lines that can be traced across continents and ocean basins. Quiet areas exist, but they exist beside intensely active ones. The surface of Earth carries a map of stress release written in recurring clusters of motion. Seen from this widest scale, the ground is neither uniformly stable nor chaotically disturbed. It is organized into provinces of greater and lesser unrest, and this organization is the visible starting point for any careful account of a possible global earthquake pattern. Beyond the first broad view of the world map, the pattern tightens around the edges of the great ocean basins and along the margins of continents. Here the line between sea and land is often more than a coastline. It is often the surface expression of a long geological boundary, where the outer shell of Earth changes character, thickness, elevation, and mechanical behavior over great distances. In these boundary regions, earthquakes become more frequent, more closely spaced, and in some places more powerful. The planet's unrest is not spread evenly across open continents or open oceans. It is drawn again and again toward margins where different parts of the surface meet. The Pacific Ocean offers the clearest example. Around much of its perimeter, the seafloor approaches continents or island arcs through deep offshore trenches and steep submarine slopes. These are not ordinary low places on the seafloor. They are among the deepest features on Earth's surface, long, narrow depressions that run for thousands of kilometers. Near them, seismic activity rises sharply. Offshore from Chile and Peru, from Central America and Mexico, from Alaska and the Aleutian Islands, from Kamchatka, Japan, the Mariana region, the Philippines, Indonesia, Tonga, and New Zealand. Earthquake records form dense bands that follow the contour of the margins. These are places where the boundary between oceanic and overriding crust is active, strained, and repeatedly broken by motion. From the surface alone, the relation is striking. Deep trench, island chain or coastal mountain belt, frequent earthquakes, even without descending below the seafloor. The geometry suggests that the ocean basin edge is not a passive rim, it is an active frontier. Ships crossing above may see only waves and weather. Coastal cities may see only harbours, beaches, cliffs, or distant peaks. Yet beneath this familiar surface, the shape of the margin marks a long-running system of compression, bending, and displacement. The earthquakes recorded there are part of that system's visible expression at the ground. Island arcs add another layer to the surface pattern. These curved chains of islands often stand just landward of trenches and parallel to them, over immense distances. Japan is one example, the Aleutians another, Tonga another, the Lesser Antilles another. Their curved form reflects the shape of the underlying plate boundary, but from the surface perspective they appear as strings of mountainous islands rising from deep surrounding water. These arcs are among the most seismically active places on Earth. Earthquakes occur offshore, beneath the islands, and inland of the arc. Some are shallow and close to the surface. Others occur deeper beneath the margin. At this outer stage of description, the important fact is that seismicity gathers not only at continental coasts but also at these oceanic arcs, where the ocean basin edge is broken into chains of elevated land. Continental margins show strong contrasts. Some are active and crowded with earthquakes. Others are broad and relatively quiet. Along the west coast of South America, the margin is narrow, mountainous, and intensely seismic. Along much of the eastern coast of South America, the continental edge slopes into the Atlantic with far less seismic activity. Western North America includes some of the most active coastal and near-coastal zones in the world, especially Alaska and the Pacific margin farther south. Eastern North America, by contrast, faces an Atlantic margin that is much quieter. These differences show that not every edge of a continent behaves in the same way. The presence of a coastline alone does not predict earthquakes. The kind of boundary beneath and offshore matters. The Indian Ocean region presents a similarly varied picture. Indonesia forms one of the most active seismic margins on Earth, with densely packed earthquakes beneath islands, seas, and adjacent ocean floor. Farther west, the northern Indian Ocean meets the complex margins of the Arabian region, Iran, Pakistan, and the Himalaya, linking offshore and continental deformation across a wide zone. Yet large stretches of other continental shores around the Indian Ocean are less active. The distribution remains selective. Earthquakes favour particular margins where the outer shell is being compressed, bent, or sheared, while bypassing others where strain release is less concentrated. Ocean basins themselves are not empty of earthquakes, but many of their strongest surface patterns still relate to margins. The deeper central parts of the basins may host activity along submerged ridges and fracture zones. Yet the most dramatic concentrations of large earthquakes gather where oceanic crust approaches another plate at the basin's rim. The basin edge, then, acts as a kind of organizing frame for much of global seismicity. On maps of major events, the eye is repeatedly drawn to coast-facing trench, arc-facing deep water, and steep offshore relief beside narrow belts of rupture. These margins matter greatly for human life because they often support dense populations. River valleys open to the sea, harbours encourage trade, volcanic soils support agriculture, coastal plains invite settlement. Yet the same margins that attract people are often the margins that accumulate strain. Cities such as Tokyo, Santiago, Lima, Manila, Wellington, and many others occupy regions shaped by long geological unrest. The earthquake pattern along continental and island margins is therefore not only a geological arrangement, it is also a pattern of repeated contact between deep planetary motion and human settlement at the edge of the sea. The sea itself can hide the exact location of rupture. A major offshore earthquake may begin beneath water far from land, with no visible sign on the surface at first. Instruments reveal what the eye cannot. This is one reason why the global pattern became clearer only as marine geophysics and seismic monitoring improved. The ocean floor is difficult to observe directly, yet over time, maps of hypocenters, or earthquake starting points below the surface, have shown that active margins beneath the sea form some of the most consistent structures in Earth science, even where no city stands nearby and no shoreline offers a reference. The seismic pattern still traces the margin with remarkable fidelity. Continental margins that are active also tend to be topographically dramatic. Coastal mountain belts rise steeply, offshore trenches plunge downward, island arcs lift sharply from deep water. These forms are the surface marks of a system that stores energy over long periods and releases some of it through earthquakes. Still, the exact timing of any one event remains difficult to predict. A quiet span of months or years along an active margin does not mean the margin has become inactive. It means that strain release is uneven in time, as well as clustered in space. Some segments rupture often in modest events, others remain locked longer and then fail in large earthquakes. The surface pattern along margins is therefore both persistent and irregular. When observers think about a possible global pattern forming on opposite sides of Earth, coastlines and ocean basin edges often provide the first visible suggestion. One large earthquake strikes near one trench, another follows months later along a distant arc. Another appears on a far continental edge facing a different ocean. The arrangement can seem balanced across the globe. Observations confirm that active continental margins and ocean basin rims host many of Earth's strongest earthquakes, and that activity in these regions may occur in separated clusters. It remains uncertain, however, whether apparent correspondence between distant margins in a limited time window reflects a connected planetary signal or the expected behavior of many active boundaries operating at once. At this second layer of view, the surface map gains sharper structure. Earthquake activity is not only concentrated in broad global belts, it is especially concentrated where oceans meet continents, where deep basins end in trenches, and where arcs of islands rise above submerged boundaries. The margins of the sea are among the principal zones where Earth's outer shell reveals its unrest. Their repeated motion shapes both landscapes and hazard, and their lines around the globe form one of the clearest outer patterns in the study of earthquakes. From the broad belts of seismicity and the active margins of ocean basins, the view narrows further toward a more exact spatial idea. The phrase opposite sides of the Earth carries a strong intuitive meaning. It suggests a planet divided by distance into paired points, where an event in one place may be compared with another as if the globe were answering itself across its full diameter. In geometry, this relation can be defined with precision. On a sphere, an antipode is the point exactly opposite another point, reached by passing through the center of the planet from one side to the other. Any location on Earth has such an opposite point, though for much of the land surface that opposite point lies in the open ocean, because the distribution of land and sea is uneven across the sphere. This spherical geometry matters because the human eye is easily impressed by broad separation without demanding exact opposition. Two earthquakes can occur very far apart and still not be close to antipodal. They can lie on different rims of the Pacific, or one in South America and one in East Asia, and appear strikingly opposed on a familiar map, while their actual relation on the sphere is only partial. Flat maps encourage this impression. They stretch and cut the curved surface of Earth into a rectangle, and in doing so they distort distance, direction, and symmetry. A pair of events that looks almost opposite on a wall map may be offset by many hundreds or even thousands of kilometers when measured on the globe itself. To define true opposition, scientists use latitude and longitude. The antipode of a point in the northern hemisphere lies at the same angular distance south of the equator, and the longitude shifts by half the circumference of the Earth in angular terms. This makes the idea exact rather than visual. Once the calculation is made, the comparison becomes less poetic and more rigorous. A point in northern Japan has an antipodal point in the South Atlantic or near South America, depending on its exact position. A point in Chile may be opposed by one in China or Mongolia, or by adjacent oceanic regions, again depending on location. Many active seismic regions do not face other active seismic regions directly. They face quiet ocean floor. This simple geographic fact immediately limits many dramatic impressions of one earthquake being answered by another on the opposite side of the world. Even so, some active belts do have partial geometric relations across great distances. The Western Pacific and parts of South America, the Mediterranean region and sectors of the South Pacific, the Himalaya and regions of the South American margin may present broad visual contrasts or rough oppositions depending on the exact points chosen. Yet the globe does not organize its active zones into neat mirrored pairs. Earthquake belts arise from the arrangement of tectonic plates, and the plates are not laid out with global symmetry. Continents cluster unevenly, ocean basins open irregularly, margins curve and break, old collisions and new spreading centers intersect at different angles. The result is a planet whose seismic geography is structured but not balanced like a perfect geometric figure. This is why the phrase a global earthquake pattern on opposite sides of the Earth needs careful handling. It may refer to several different things. It may mean strict antipodal pairing, where events occur near exact opposite points. It may mean looser far-side correspondence, where active periods appear in separated belts divided by a large fraction of the globe. It may mean the perception that when one side of the planet is seismically busy, another distant sector also becomes active within the same general period. These are not the same claim. The first is a geometric claim. The second is a broad spatial observation. The third mixes space with time and suggests possible linkage. Much confusion arises when these meanings are blended together without definition. At the purely spatial level, opposite-side geometry is easiest to test. One can take an earthquake epicenter, which is the surface point above where rupture begins, and calculate its antipode. Then one can ask whether the opposite region is also active, whether it lies near another seismic belt, or whether it is mostly quiet. In many cases, the opposite region will not show any special relation at all. It may sit in a stable oceanic area, far from major boundaries. In other cases, it may fall near an active margin or ridge system. Because Earth's active belts are long and curved, some degree of distant correspondence can appear by chance. If enough earthquakes occur across enough active zones, a few will always seem to line up in suggestive ways. The shape of the Earth itself influences perception here. A sphere allows any long arc to seem connected to another if the eye seeks balance. The human mind is skilled at pattern finding. This skill is useful in science because it helps observers notice regularity. But it also invites overinterpretation. On a global earthquake map crowded with points, some events will appear to form lines, clusters, or opposite pairs simply because the dataset is large. Scientific caution therefore begins with geometry. Before asking whether distant earthquakes are linked, one must first ask whether they are truly opposite in a measurable sense, or whether they are only widely separated. Distance alone does not imply a special physical relation. Two regions can be nearly half a world apart yet belong to unrelated tectonic systems. One may lie along a subduction margin, where one plate descends beneath another. Another may lie in a continental collision zone. Another may sit near a spreading ridge. Their great separation gives them visual drama, but their mechanics may be entirely different, even if activity occurs in both regions within the same year. The geometry does not by itself provide evidence of a shared cause. It provides only the spatial frame in which a comparison can be made. There is also the problem of scale. A great earthquake affects a fault zone that may extend for hundreds of kilometers, while its antipodal region, if defined exactly, is a point or a limited nearby area on the sphere. If one broadens the definition to include a wide surrounding zone, apparent matches become easier to find. If one keeps the definition narrow, true matches become rarer. Thus, the claim of opposite-side pattern depends strongly on how much spatial tolerance is allowed. A difference of a few degrees on the globe represents a large physical distance at the surface. What seems close on a small world map may be far apart in actual terms. Observations indicate that some large earthquakes generate seismic waves that travel through the entire Earth and can be detected worldwide, including near antipodal regions. This fact gives the idea of opposite-side relation a real physical setting, though not yet a proof of recurring paired seismicity. It remains uncertain whether repeated sequences of strong events in roughly opposite sectors reflect more than the active background of Earth's major seismic belts. The globe provides the geometric possibility of such patterns, but geometry alone cannot establish process. At this stage, the outer inquiry becomes more precise. The idea of opposite sides of the Earth is no longer a loose impression drawn from a map. It becomes a measurable relation on a sphere, one that often reveals less symmetry than first appears. Earth's seismic belts are real, but they are not arranged as perfect counterparts across the planet. Any claim of a forming global pattern must therefore begin with careful geometry, separating exact antipodes from broad separation and broad separation from meaningful connection. Only then can the surface arrangement be described without illusion, and only then can the world-spanning image of paired unrest be judged against the actual shape of the Earth. After the geometry of the planet is considered, attention turns from space to time. Earthquakes do not only occupy places, they unfold within intervals, some brief, some extended, all measured against the continuous passage of days, months, years, and longer spans. The idea of a global pattern depends not only on where earthquakes occur, but also on when they occur. A pair of distant events separated by many years carries a different meaning from a pair separated by hours or days. To examine whether a pattern may be forming, scientists look carefully at time windows, defining how long an interval must be before a grouping of earthquakes can be judged as meaningful rather than coincidental. At the shortest scale, earthquakes appear as sudden events. A fault ruptures, energy is released, and seismic waves spread outward in seconds to minutes. Instruments record the motion with great precision. In this immediate sense, each earthquake is a discrete occurrence. Yet even at this shortest scale, many earthquakes are not isolated. They belong to sequences. A large earthquake is often followed by aftershocks, smaller events that occur as the crust adjusts to the new distribution of stress. These aftershocks may continue for days, months, or even years, gradually decreasing in frequency. At the surface, this creates a cluster in both space and time. A single fault segment may remain active for a prolonged period after the initial rupture. When the time window widens from minutes and hours to days and weeks, more complex patterns emerge. Separate earthquake sequences in different regions may overlap in time, while one margin experiences a large event and its aftershocks. Another margin may undergo its own sequence. Because the Earth is always active at some level, the probability that two or more regions experience earthquakes within the same short interval is not low. This overlapping activity can create the impression of coordination across distances. Yet at this scale, the overlap may reflect the independent behavior of multiple active systems rather than a shared trigger. Extending the window further to months and years allows for the comparison of broader seismic trends. Scientists examine catalogues of earthquakes, looking for periods of increased global activity or for clusters of large events occurring within relatively short spans. Historical records show that some years include several large earthquakes in different parts of the world, while other years are quieter in terms of major events. This variation raises the question of whether Earth sometimes enters phases of heightened global seismicity. Observations indicate that there are fluctuations in the rate of large earthquakes over time. It remains uncertain whether these fluctuations represent true global cycles or are consistent with random variation in a system that produces rare but powerful events. The concept of clustering becomes more subtle at these longer scales. A cluster is a grouping of events closer together in time than expected from a uniform distribution. Detecting such clustering requires statistical analysis. Scientists compare observed sequences with models that assume earthquakes occur randomly at a given average rate. If the observed clustering exceeds what would be expected by chance, it may suggest underlying processes that link events. However, because large earthquakes are infrequent, the available data are limited. A few decades of detailed global records may include only a small number of the largest events. This makes it difficult to distinguish a real pattern from a random grouping with high confidence. When the time window extends to decades and centuries, the record becomes even more complex. Historical accounts, geological evidence, and modern measurements must be combined. Some regions show recurring large earthquakes on timescales of tens to hundreds of years, reflecting the slow accumulation and release of strain along specific faults. When several such regions happen to produce large events within overlapping decades, a global pattern may seem to emerge. Yet each region follows its own cycle, influenced by local conditions. The alignment of these cycles across distant parts of the planet may occur occasionally without implying a direct connection. Temporal analysis also involves the concept of recurrence intervals. This term describes the average time between large earthquakes on a given fault or in a given region. Recurrence intervals are not exact schedules, they are estimates derived from past events. Some intervals may be shorter, others longer. When multiple regions with similar recurrence intervals approach the end of a typical cycle, the likelihood of several large earthquakes within a limited period may increase. This can produce a temporary impression of synchronized activity across the globe. Observations indicate that such overlaps are possible. It remains uncertain whether they represent coordinated behavior or simply the intersection of independent cycles. Another important aspect of time is the difference between short-term triggering and long-term independence. In some cases, a large earthquake can influence nearby faults, increasing or decreasing the likelihood of subsequent events in the same region. This influence usually operates over distances of tens to hundreds of kilometers and over timescales of days to years. When considering opposite sides of the Earth, the distances are far greater. Any temporal relation between distant events would need to be evaluated against the background rate of global seismicity. If two large earthquakes occur within a few days on widely separated margins, the coincidence may appear striking, yet without repeated occurrences of such timing, it is difficult to establish a consistent pattern. The role of perception is also important. Human attention tends to focus on large, damaging earthquakes, especially those reported widely in news and communication networks. When several such events occur within a short period, they can create a sense of escalation or global unrest. However, smaller earthquakes continue constantly around the world, often unnoticed. The apparent increase in activity may partly reflect selective attention rather than a true change in the underlying process. Careful temporal analysis requires consideration of the full range of events, not only the most visible ones. Modern seismic networks provide a continuous global record, allowing scientists to analyze time patterns with increasing detail. Automated systems detect and locate earthquakes across the planet, building extensive catalogues. These data enable comparisons across different time windows and regions. Statistical methods can test whether observed sequences deviate from expectations based on known rates. So far, studies suggest that while regional clustering and aftershock sequences are well established, evidence for strong global synchronization of large earthquakes is limited. Observations indicate variability in global activity over time. It remains uncertain whether this variability reflects underlying global processes or the inherent randomness of rare events. At this temporal layer, the investigation becomes a balance between observation and interpretation. Time windows can be chosen narrowly or broadly, each choice revealing different aspects of the data. Narrow windows highlight immediate sequences and local interactions. Broad windows reveal long-term trends and possible overlaps between distant regions. A perceived global pattern on opposite sides of the Earth depends strongly on the selected interval. A short interval may emphasize coincidence. A long interval may dilute apparent connections. The challenge is to identify patterns that persist across multiple scales of time, rather than those that appear only within a specific window. The surface map of earthquakes gains depth when time is added. Events that seem isolated in space may belong to sequences in time. Events that appear paired across distance may simply share a common period of occurrence within a continuously active system. The Earth does not release its stored strain in a steady rhythm. It does so in uneven pulses, varying from place to place and from year to year. Within this variability, patterns can be suggested, but each must be tested against the full record. The possibility of a forming global pattern cannot be judged by a few events within a brief span. It requires sustained observation across many intervals, careful comparison with expected behavior, and cautious interpretation of what is known and what remains uncertain. Beneath the shifting pattern of time and the visible arrangement of surface activity lies a more fundamental layer, one that explains why earthquakes gather where they do. The outer shell of the Earth is not a single unbroken piece. It is divided into large sections known as tectonic plates. Each plate is a vast slab of solid rock, composed of crust and the uppermost part of the mantle, moving slowly across the surface of the planet. This motion is not rapid in human terms. It proceeds at rates measured in centimeters per year, comparable to the growth of a fingernail. Yet over millions of years, these slow movements reshape continents, open oceans, and bring plates into contact with one another. The arrangement of these plates forms the underlying structure of the global earthquake pattern. The Pacific Plate, one of the largest, is surrounded by several smaller plates and continental masses. Its boundaries trace much of the Ring of Fire, where earthquakes are most frequent. The Eurasian Plate extends across Europe and Asia, meeting other plates along complex margins. The African Plate, the North American Plate, the South American Plate, the Antarctic Plate, and the Indo-Australian Plate each occupy large regions of the globe. Between them lie additional plates and smaller fragments, each contributing to the overall mosaic. At the surface, these plates are not visible as separate units. There are no clear lines painted across continents or oceans to mark their edges. Instead, their presence is inferred from patterns of earthquakes, volcanic activity, and precise measurements of ground motion. Instruments placed on the Earth's surface can detect the slow drift of continents relative to one another. Over time, these measurements reveal that the plates are indeed moving, each following its own path. Sometimes converging, sometimes diverging, sometimes sliding past adjacent plates. Where plates meet, stress builds in the rock. Because the plates are rigid over large scales, they do not flow smoothly past one another at their boundaries. Instead, they become locked by friction. As the plates continue to move, strain accumulates along the boundary. This strain represents stored energy within the rock. When the stress exceeds the strength of the material, the boundary fails, and the stored energy is released suddenly as an earthquake. This process explains why earthquakes are concentrated along plate boundaries. It is not the presence of a coastline or a mountain alone that matters. It is the interaction between moving plates beneath those features. The movement of plates is driven by processes deep within the Earth, including the slow flow of material in the mantle. Heat from the planet's interior causes convection, a gradual circulation in which hotter, less dense material rises and cooler, denser material sinks. This movement exerts forces on the base of the plates, helping to drive their motion across the surface. In addition, the weight of sinking plates at some boundaries pulls them downward, contributing further to motion. These forces operate continuously over geological time, maintaining the dynamic system that produces earthquakes. The direction and speed of plate motion vary from one boundary to another. Some plates move toward each other, compressing the boundary between them. Others move apart, creating new space that must be filled by rising material from below. Still others slide past each other, with lateral motion dominating. Each type of movement produces its own pattern of stress and its own style of earthquake activity. Yet at this level, the key idea remains simple. The plates move, the boundaries resist. Stress accumulates, and earthquakes release that stress in sudden adjustments. This framework provides a deeper explanation for the surface patterns observed earlier. The Ring of Fire corresponds to the boundaries of the Pacific Plate, where it interacts with surrounding plates. The Mediterranean to Himalayan belt reflects the collision and complex interaction between the African, Arabian, and Eurasian plates. Oceanic ridges mark the places where plates move apart. Stable continental interiors correspond to regions far from active boundaries, where stress accumulation is slower and less concentrated. The plate structure organizes the entire surface pattern of earthquakes into a coherent system. Despite this organization, the motion of plates is not perfectly smooth or uniform. Some boundaries experience frequent small earthquakes, releasing strain gradually. Others remain locked for long periods, accumulating large amounts of stress that are released in powerful events. The behavior of each boundary depends on factors such as rock type, temperature, pressure, and the presence of fluids. These local conditions influence how strain is stored and how it is released. As a result, even within the global plate framework, the timing and size of earthquakes remain variable. The concept of moving plates also clarifies why distant regions can appear active at the same time without being directly connected. Each plate boundary operates within the broader system, but its behavior is largely controlled by local conditions and interactions. When several boundaries release stored strain within a similar period, the result can be a series of earthquakes across different parts of the world. This does not necessarily imply that one event causes another across vast distances. It reflects the fact that many boundaries are continuously accumulating stress and may reach failure at different times. Observations indicate that plate motion is steady over long periods, but earthquake occurrence is irregular. This contrast is important. The plates do not stop and start in response to earthquakes. They continue to move at roughly constant rates. Earthquakes represent the episodic release of strain along boundaries that are otherwise locked. Because the release is uneven in time, clusters of earthquakes may occur in some periods, while other periods remain relatively quiet. This variability can create the impression of changing global patterns, even though the underlying motion of the plates remains consistent. At this level of understanding, the idea of a global earthquake pattern on opposite sides of the Earth must be considered within the context of plate tectonics. The plates define where earthquakes are most likely to occur, and their independent motion explains why activity can be distributed across the globe without direct linkage. While it is possible for distant regions to experience earthquakes within the same time window, the plate framework suggests that such occurrences are often the result of separate processes acting within different parts of the system. The surface pattern of earthquakes gains clarity when seen through the lens of moving plates. The apparent complexity of global seismicity resolves into a network of boundaries, each carrying its own share of strain. These boundaries encircle ocean basins, cross continents, and extend beneath the sea. Together, they form the structure upon which all earthquake activity is built. Understanding this structure is essential before considering deeper layers, where the nature of stress, rock behavior, and internal processes further shape the distribution and timing of earthquakes. Where tectonic plates meet, their slow motion is translated into pressure, tension, and friction. These forces do not appear directly at the surface as visible currents or flowing streams. They build quietly within the rock, over years, centuries, and longer spans, as one plate presses toward another, pulls away from another, or slides beside another. The result is stress, the force applied to rock, and strain, the deformation that rock experiences under that force. These terms describe the physical condition of the crust before an earthquake occurs. At plate boundaries, stress is not distributed evenly. It concentrates along surfaces of weakness and along irregular contacts, where resistance prevents smooth movement. The earthquake begins when that resistance is overcome. There are three main kinds of plate boundary. At convergent boundaries, plates move toward each other. At divergent boundaries, they move apart. At transform boundaries, they slide laterally past one another. Each type of boundary creates a different stress environment and a different pattern of seismicity. This variety explains why earthquakes do not all look the same on global maps, why some occur in narrow, deep belts and others in shallower linear zones, and why some regions produce enormous earthquakes while others mostly release energy in smaller frequent events. At convergent boundaries, compression dominates. One plate approaches another, and the rock between them is shortened, thickened, or forced downward. Along many oceanic margins, one plate descends beneath another. But at this stage the essential fact is simpler than the deeper geometry. These are boundaries of crowding and resistance. The rocks are pushed together, bent, fractured, and held by friction, because the opposing motions continue year after year. Large amounts of elastic strain can accumulate. Elastic strain means reversible deformation, like a spring being slowly compressed or bent. Rock behaves like this over long intervals until it fails. When failure occurs after long accumulation, the resulting earthquake can be very large. Compression also produces broad zones of faulting and folding near the boundary. Some of these structures break in shallow earthquakes close to the surface. Others extend deeper and produce earthquakes over a wider range of depths. The surface expression may include trenches offshore, uplifted coastlines, mountain belts, and deformed sedimentary basins. Yet beneath these features, the common element is compressive stress. The boundary resists motion until rupture occurs. The more strongly it is locked and the longer strain accumulates, the greater the possible release when failure comes. At divergent boundaries, the stress field is different. Here the plates move apart, and tension dominates. Tension is a pulling force that stretches a rock and can thin it until it fractures. As the boundary opens, cracks and normal faults develop. A normal fault is a break in which one side moves downward relative to the other under extension. Earthquakes at divergent boundaries are generally shallower than those at many convergent margins, because the stress is concentrated in the upper part of the crust where brittle fracture can occur under stretching. These earthquakes are often smaller than the largest compressional earthquakes, yet they can be numerous and persistent, especially along active ridge systems and continental rifts. The rock at divergent boundaries is also warmer on average than at many convergent margins, because these boundaries are associated with rising material from below and with the formation of new crust. Warmer rock tends to deform more easily at depth, which limits how deep brittle fracture can extend. For this reason, the earthquake zone at divergent boundaries is often narrow in depth, even when it is long in horizontal extent. The stress is real and continuous, but the style of rupture differs from that of more strongly locked compressional boundaries. At transform boundaries, shear stress dominates. Shear is a force that causes adjacent parts of rock to move sideways relative to one another. Instead of being pushed together or pulled apart, the blocks are dragged laterally in opposite directions. Friction along the boundary prevents constant smooth sliding. As with other boundaries, a strain accumulates until the resistance is exceeded. Then the fault slips suddenly, producing an earthquake. Transform earthquakes are often shallow, because the slipping surface lies within the brittle upper crust. they can still be very destructive, especially where the fault runs near cities or through populated basins. Shear boundaries often produce long straight fault traces, offset streams, narrow valleys, and linear scarps. At the scale of stress, their importance lies in the way motion is partitioned. The total relative movement of two plates may be spread across one main fault or divided among several faults within a broader zone. This distribution influences how earthquakes recur. Some segments may rupture frequently in moderate events. Others may remain locked longer and fail in larger earthquakes. The surface line may appear simple, but the stress field along it is often complex. These three boundary types are ideal categories, yet in nature many boundaries combine elements of more than one. Oblique convergence, for example, includes both compression and lateral shear. A curved plate margin may change character along its length, behaving more like a transform boundary in one segment and more like a convergent boundary in another. Continental collision zones can contain numerous faults with different motions operating at once. This means that the stress environment is rarely uniform over great distances. Instead, each boundary is a mosaic of local conditions shaped by the broader direction of plate motion. Stress also changes through time. A boundary segment may remain locked for decades or centuries, storing elastic strain. Then an earthquake redistributes that stress. Some nearby faults may be brought closer to failure. Others may be moved farther from it. This redistribution creates patterns of aftershocks and can alter the local seismic hazard after a major event. However, the change usually diminishes with distance. At the global scale, each boundary still primarily reflects its own long-term loading from plate motion. This is why widespread earthquake activity can occur in different parts of the world without requiring a single unified stress pulse acting across the entire planet. Observations indicate that boundary type strongly influences earthquake depth, frequency, and maximum size. Convergent boundaries produce the largest earthquakes known. Divergent and transform boundaries more often produce smaller and shallower events, though some can still be severe. These differences help scientists interpret global patterns. If several large earthquakes occur in distant convergent zones within a limited period, the similarity in setting may seem suggestive. Yet the shared boundary type does not itself prove a common trigger. It shows that these are places where large strain naturally accumulates. At this level, the global pattern of earthquakes becomes more physically grounded. The map is not only a set of active lines, it is a map of different mechanical environments. Some boundaries are zones of compression, some of extension, some of shear, and many of mixed behavior. Each environment governs how rock stores energy and how it fails. The apparent pattern of earthquakes across the world is therefore a pattern of stress release shaped by the way plates meet. What appears at the surface as scattered episodes of shaking is, at the boundary scale, the consequence of persistent forces acting through contact, resistance, and eventual rupture. Inside the moving outer shell of the planet, stress does not spread through perfect, unbroken stone. It moves through crust that is already fractured, layered, folded, buried, uplifted, heated, cooled, and altered by long histories of pressure and motion. The crust is the thin outer rock layer of Earth, thinner beneath oceans and thicker beneath continents, and within it lie faults, the breaks along which blocks of rock can slip past one another. These faults are not rare exceptions. They are fundamental structures of the crust, produced over immense spans of geological time. Some are active now, some have been quiet for long intervals, some are visible at the surface as scarps, valleys, or offset ridges. Others are buried beneath sediment. Cities, forests, or the seafloor. Together they form the fractured architecture through which much earthquake energy is released. A fault begins as a zone of weakness, often created when rock is placed under stress greater than its strength. Once a fracture forms, later motion tends to return to that same surface or to nearby related fractures, because the rock there is already broken and weaker than the surrounding mass. In this way, faults can persist through repeated episodes of movement. A region may therefore contain a whole network of old and young faults, some linked, some separate, all embedded within rock that remembers earlier deformation. The crust is not reset after each earthquake. It carries forward the effects of what came before. This matters because plate boundaries are broad in geological terms. Even where the overall line of contact between plates is known, the actual movement is often distributed across many faults within a wider zone. Compression may be taken up by thrust faults, which are breaks where one block is pushed up over another. Extension may be taken up by normal faults, where one block drops downward. Shear may be taken up by strike-slip faults, where blocks move sideways past one another. These forms are the visible mechanical pathways by which stress becomes motion. The large-scale pattern of plate movement is translated into the local scale of earthquakes through the existence and behavior of these faults. A single earthquake usually begins on only part of a fault, or on one fault within a larger system. The rupture then spreads along the broken surface as the rock gives way. Some ruptures remain short and produce modest earthquakes. Others cascade across long segments and produce major events. The length, shape, roughness, and connectivity of a fault all influence how far rupture can travel. If a fault is strongly segmented, with bends or steps that resist rupture, an earthquake may stop after limited motion. If several segments are well connected, rupture may continue across a much greater distance. Thus, the crust's fractured structure does not merely locate earthquakes, it also helps govern their size. Fault zones are rarely simple planes. They often consist of crushed rock, branching fractures, mineral veins, pockets of trapped fluid, and irregular surfaces that lock and unlock in uneven ways. This complexity helps explain why stress can accumulate for long periods even on a known fault. Different patches along the same fault may behave differently. One area may creep slowly, slipping without large earthquakes. Another may remain locked and store strain. Another may rupture repeatedly in small events. When a large earthquake occurs, these varied patches interact. Some break, some resist, some are changed by the passing rupture. The crust therefore behaves less like a smooth machine and more like a rough, heterogeneous structure with many local differences. In continental regions, faults may extend for hundreds of kilometers across mountain belts, plateaus, basins, or plains. Some are obvious in the landscape. Others are concealed beneath young sediment and only detected through geophysical surveys. Trenching, or the pattern of small earthquakes. In oceanic crust, faults also occur, though they are hard to observe directly. Along ridges, transform boundaries, and subduction-related settings. The ocean floor is cut by fractures that guide earthquake occurrence beneath the sea. Whether beneath continents or oceans, the crust fractures because it cannot permanently absorb unlimited stress without breaking. The temperature and pressure conditions of the crust affect how faults behave. In the cooler upper crust, rock tends to break in a brittle manner, meaning it fractures rather than flowing. Most damaging earthquakes occur in this brittle zone, where sudden rupture is possible. At greater depths, increasing heat and pressure make many rocks deform more gradually, bending or flowing over long periods instead of breaking abruptly. This transition limits the depth range of many crustal earthquakes. It also means that the upper crust contains the main broken framework through which ordinary shallow seismicity is organized. Fluids play an additional role inside fault zones. Water and other fluids within pores and cracks can reduce the effective pressure that holds fault surfaces together. When this happens, slipping may become easier. Fluids can enter fault zones from deep metamorphic reactions, from surface infiltration, or from nearby sedimentary basins. Their movement is difficult to track directly, but observations indicate that fluid pressure can influence earthquake timing and fault strength in some settings. This does not mean fluids create the large-scale earthquake pattern by themselves. Rather, they modify the behavior of already stressed faults within the fractured crust. Older faults can remain important long after the tectonic setting that formed them has changed. A continent may carry ancient zones of weakness from past rifting, collision, or shearing. When present-day stress acts on the crust, these inherited structures may be reactivated. This is one reason why earthquakes can occur in places far from present plate boundaries. The crust stores not only current stress but also old damage. Its fracture pattern reflects both the forces of today and the structures left by ancient episodes of deformation. A global map of earthquakes therefore overlies a much older hidden map of crustal scars. When distant earthquakes appear to form a broad pattern across the world, each event still depends on the local existence of a fault capable of rupture. No global arrangement can bypass this basic fact. A major earthquake cannot occur where there is no suitably stressed and structured fault system to fail. Even if broad processes influence stress at large scales, the actual event must be rooted in the fractured crust of a specific place. This is why the study of possible global patterns always returns to fault architecture. Large distance does not erase local control. The rupture begins in one fault zone, within one set of broken rocks, under one combination of stress and resistance. Observations indicate that faults are the immediate structures through which most tectonic earthquakes occur, and that crustal complexity strongly influences rupture behavior. It remains uncertain in many cases exactly how fault roughness, fluids, and inherited weakness combine to determine the timing of failure on a given segment. What is clear is that the crust is not a smooth shell. It is a fractured medium filled with old and active breaks, and these breaks channel the release of strain in uneven but understandable ways. At this inner stage of the journey, the global earthquake pattern resolves into individual pathways of failure. The moving plates provide the broad framework, but the fractured crust provides the actual surfaces of slip. Faults divide the rock into blocks, store the marks of ancient stress, and determine where present stress is most likely to be released. Earthquakes are therefore not only expressions of planetary motion, they are also the direct consequence of a crust already broken, already weakened, and always being tested again by the slow forces acting through it. Where the fractured crust enters its most compressed and deformed surface systems, the landscape rises into mountain belts or bends downward beside deep marine trenches. These are the regions where plate motion is not only stored within faults, but expressed through vast zones of descent, uplift, folding, thickening, and repeated rupture. Mountain belts and subduction zones belong to the same broad family of convergent settings, yet they appear in different forms depending on whether oceanic crust sinks beneath another plate, or whether buoyant continental masses press against one another. In both cases, earthquakes become especially important because the crust and uppermost mantle are forced into sustained contact under great stress. A subduction zone is a boundary where one tectonic plate, usually carrying dense oceanic crust, moves beneath another plate and descends into the mantle. At the surface, this arrangement often creates a trench offshore and a chain of mountains or volcanoes inland. The descending plate does not sink smoothly like a rigid board sliding beneath a carpet. It bends, locks against the overriding plate, scrapes sediments, deforms the forearc region, and carries stress into deeper levels. Because of this, earthquakes occur across a broad three-dimensional system rather than along a single shallow line. Some happen near the trench, others occur farther inland, others happen deeper within the descending slab. The upper part of a subduction zone is often the site of the largest earthquakes on Earth. Here the descending and overriding plates may remain locked together over enormous areas. Plate motion continues, but the boundary resists slipping. As years and centuries pass, the outer edge of the overriding plate may be slowly dragged toward the trench and downward, storing elastic strain across a wide region. When that locked interface finally fails, the release can involve hundreds of kilometers of fault length and great displacement. These are the earthquakes that can raise or lower coastlines, shake city across wide regions, and in some cases displace the seafloor enough to generate tsunamis. This setting helps explain why certain mountain-lined coasts and island arcs are repeatedly associated with extreme seismic hazard. Chile, Alaska, Japan, Sumatra, and parts of the Southwest Pacific occupy such zones. Their mountains are not incidental scenery beside an otherwise simple boundary. They are part of the long surface expression of ongoing convergence. Sediments are compressed and scraped off. Crust is shortened and uplifted. Faults within the overriding plate also break under the strain imposed by the larger system. In this way, the visible relief of the land and the invisible storage of elastic energy are linked. In continental collision belts, the setting differs, yet the stress remains intense. Here, two continents, each relatively buoyant, converge so that neither descends easily into the mantle in the same way as dense oceanic crust. Instead, the crust thickens, folds, faults, and rises into broad, high topography. The Himalaya and the Tibetan region provide the clearest modern example. The motion between India and Eurasia has produced one of the largest elevated regions on Earth. Earthquakes in such settings often occur on major thrust faults, crustal scale strike-slip faults, and deeper structures within the thickened crust. The mountain belt is therefore not merely the consequence of ancient compression, it is an active zone where stress continues to accumulate and release. These mountain systems contain many interacting faults rather than one single boundary surface. Some faults carry motion by pushing one rock mass over another. Others accommodate sideways escape of crustal blocks. Others break within the interior of the plateau or along the front of the range. This complexity means that seismicity in continental collision zones may be distributed over a broader area than in some oceanic subduction margins. Yet the common thread remains convergent stress and large-scale crustal deformation. The high topography reflects crust that has been shortened and thickened over long periods, and the earthquakes reflect that the process remains active. Subduction zones and mountain belts also share a connection to material contrast. In oceanic subduction, dense seafloor crust and upper mantle descend beneath a less dense overriding plate. In continental collision, thick buoyant crust resists descent and instead piles up. These differences affect the geometry of faults, the depth range of earthquakes, and the shape of the surface. But in both settings, the rock is forced beyond quiet adjustment. It is bent, fractured, and displaced under persistent convergence. Earthquakes become one of the main ways the system releases part of that stored energy. The surface features of these regions often reveal active deformation even between large earthquakes. River terraces may be uplifted. Coastal platforms may rise unevenly, sedimentary basins may tilt, mountain fronts may advance over adjacent plains. In some areas, careful measurement with satellite geodesy shows the ground slowly moving by a few millimeters or centimeters each year, even when no major earthquake is occurring. This slow deformation is the visible sign of strain accumulation. It shows that the boundary is loading continuously. The absence of daily shaking does not mean the system is at rest. It means the stress is being stored in rock that has not yet failed. In subduction settings, not all earthquakes occur on the main plate interface. Some happen within the descending plate as it bends before going under the trench. Others occur within the overriding plate, which is compressed, stretched, or sheared by the interaction. This creates layered seismicity across the margin. Near the surface, offshore faults may rupture in the accretionary wedge, the zone where sediments are scraped from the descending plate and deformed into ridges and folds, inland. Crustal faults may break within the volcanic arc or forearc. Deeper still, earthquakes may trace the path of the sinking slab. The subduction zone is therefore a full seismic province rather than a single fault. In large mountain belts, erosion and uplift work together over long spans. Rain, glaciers, rivers, and weathering wear material away from the rising terrain, while tectonic compression continues to drive new uplift and faulting. The mountains seen today are thus part of a moving balance between construction and removal. Earthquakes belong to the construction side of that balance. They help adjust crustal blocks, shift fault planes, and maintain the structure of the range. Even when erosion softens the surface, the deeper forces remain active. When observers notice strong earthquakes in widely separated mountainous or subduction-dominated regions within the same general period, the pattern can appear especially compelling. One great event along a Pacific trench, another in a distant collision belt, another beneath an island arc, all seem to speak of a planet under shared tension. Observations confirm that these settings are among the most likely places for powerful earthquakes because they store large amounts of compressive strain. It remains uncertain, however, whether activity across such distant convergent systems in limited time windows reflects global coordination or the independent release of stress in multiple long-loaded regions. At this deeper layer of the outer shell, the earthquake pattern becomes concentrated within Earth's strongest belts of deformation. Mountain belts show where crust thickens and rises. Subduction zones show where one plate descends beneath another and locks over immense areas. In both, stress is sustained, faults are numerous, and the potential for severe rupture is high. The visible grandeur of mountains and the hidden geometry of descending slabs are bound together by compression, resistance, and sudden release. These are not separate scenic settings on the planet's surface. They are some of the principal engines of earthquake activity, where the restless architecture of convergence becomes most intense, away from the great trenches and compressed mountain fronts. The outer shell of the Earth also breaks where it is being pulled apart. These regions do not usually carry the same public image as subduction zones, because they are often hidden beneath the oceans or spread across remote continental interiors. Yet they are essential parts of the global seismic system. Mid-ocean ridges and rift systems mark places where plates diverge, meaning they move away from one another, and where the crust responds by stretching, thinning, fracturing, and opening. Earthquakes in these settings are generally shallower than those in many convergent zones, but they are widespread, persistent, and closely tied to the creation of new crust and the reshaping of old continental regions. A mid-ocean ridge is a long submarine mountain chain that runs through the world's oceans. These ridges are not isolated peaks, They form a connected global system extending for tens of thousands of kilometers across the Atlantic, Indian, Southern, and parts of the Pacific Oceans. Along their axes, hot material rises from below, pressure decreases, and melting can occur, feeding volcanism and the formation of new oceanic crust at the surface of the seafloor. This process creates a raised ridge because the hot lithosphere there is less dense and more buoyant than the older, cooler crust farther away. The ridge is therefore both a topographic feature and a tectonic boundary. Where plates diverge along a ridge, the crust is placed under tension. The brittle upper part of the lithosphere fractures into normal faults, and small to moderate earthquakes occur as blocks drop, tilt, and adjust to the opening boundary. Because the rock is warm near the ridge axis, brittle failure is limited to relatively shallow depths. This gives ridge earthquakes a characteristic pattern. They tend to occur close to the surface compared with the deeper earthquakes of subduction systems. Their magnitudes are often smaller than the largest compressional events, but their occurrence is continuous across the global ridge network. In this sense, the opening seams of the seafloor form one of the most extensive seismic provinces on Earth. Mid-ocean ridges are not smooth, uninterrupted lines. They are segmented by offsets and linked by transform faults, where adjacent ridge sections are laterally displaced. Along these transform segments, shear replaces simple extension, and earthquakes can be more concentrated and sometimes larger than those directly on the spreading axis. This means the ridge system combines different styles of stress in close proximity. Extension dominates at the spreading center itself, while shear dominates along the connecting transforms. The overall pattern remains one of crustal opening, but the local details of rupture vary according to the geometry of the segmented ridge. The Atlantic Ocean offers a clear example. The mid-Atlantic ridge runs roughly north to south through the basin, dividing it into eastern and western halves. Earthquakes occur along its length, many of them too remote to be felt by people because they lie far beneath open water. Yet instruments record them steadily. They mark the quiet but persistent creation of new seafloor as Europe and Africa slowly move away from the Americas. The Indian Ocean contains similar spreading systems, with ridges intersecting in complex triple junction regions. In each case, the basic process is the same. The plates separate, the lithosphere fractures, magma rises, and shallow earthquakes accompany the extension. Continental rifts represent a related but distinct setting. A rift is a region where continental crust is being stretched and pulled apart. Unlike the oceanic ridges, which lie mostly beneath the sea and produce new oceanic crust, continental rifts begin within thick continental lithosphere. As stretching continues, the crust thins, large normal faults develop, and long basins form between uplifted fault blocks. Over sufficient geological time, a mature continental rift can evolve into a new ocean basin. In its earlier stages, however, it remains a land-based system of extension, sedimentation, volcanism in some places, and repeated shallow earthquakes. The East African Rift is the best-known modern example. It extends through eastern Africa in a broad system of valleys, fault scarps, lakes, volcanic centers, and uplifted shoulders. Earthquakes occur as the crust is stretched and broken into separate blocks. Some are modest and frequent, others are stronger and capable of significant local damage. The rift shows that earthquakes do not require plates to collide in order to be important. They can also accompany the slow tearing apart of a continent. The surface expression is different from a trench or mountain belt. Instead of compression and shortening, there is subsidence, fault-bounded basins, and elongated valleys. Yet the common element remains stress exceeding rock strength. Other continental rifts include the basin and range region of western North America, where extension has produced alternating mountain ranges and basins, and parts of northern Europe and Asia, where older rift systems remain tectonically significant. Some rifts are active but slow. Others are ancient and largely quiet. Active rifts reveal that divergent plate processes are not confined to the ocean floor. They can begin on land, under inhabited landscapes, and over vast regions that may not at first appear to belong to a major plate boundary. The earthquakes of spreading centers and rifts usually do not reach the deepest levels seen in subduction zones, because the stretching environment is associated with relatively high temperatures, and because brittle fracture is concentrated in the upper crust and uppermost lithosphere. This does not make them unimportant. Their shallowness can increase local shaking intensity, and their repeated occurrence reveals where the Earth is making and remaking its outer shell in oceanic settings. These earthquakes are part of the birth of new crust. In continental settings, they are part of the gradual division of existing crust into separate blocks that may one day become new plate boundaries. Rift systems also demonstrate that the global earthquake pattern includes places of construction as well as places of destruction. At subduction zones, older lithosphere descends and is recycled into the mantle. At spreading centers, new lithosphere forms. The planet's surface is therefore renewed through a balance of sinking and opening. Earthquakes occur in both environments, but with different depth ranges, sizes, and structural styles. The ridges and rifts are the outward signs of this extensional side of the system. When people look for a pattern of earthquakes across opposite sides of the Earth, spreading centers may be overlooked because many lie under distant oceans, yet they contribute continuously to the global seismic background. A strong earthquake on a subduction margin may draw wide attention, while a sequence of ridge earthquakes passes almost unnoticed except in scientific records. Observations indicate that divergent boundaries and rift systems produce abundant shallow seismicity closely linked to extension and faulting. It remains uncertain whether activity in such regions has any regular time relation to distant earthquakes in convergent settings beyond what would be expected in a planet where many tectonic systems are active at once. At this stage of the inward path, the earthquake map broadens again in meaning while narrowing in mechanism. Not all seismic belts are zones of collision. Some are the open seams of the Earth, where the crust stretches, breaks, and makes room for new material from below. Mid-ocean ridges and continental rifts show that the restless outer shell does not only compress and descend, it also parts, thins, and rebuilds itself. Their earthquakes are the shallow signatures of that opening process, written along the long hidden ridges of the sea and across the slowly widening valleys of the continents. Beyond the well-defined boundaries where plates meet, there are regions that lie within the interior of a single plate, far from trenches, ridges, or major transform faults. These areas are often described as stable in comparison with active margins, yet they are not entirely free from earthquakes. Within these intraplate regions, seismic events occur less frequently, but when they do occur, they can be unexpected and, at times, significant. The presence of these earthquakes reveals that the Earth's crust retains stresses even far from the edges where plates interact directly. Intraplate earthquakes originate within the interior of tectonic plates, often along ancient zones of weakness. These zones may be remnants of earlier geological events such as past collisions, rifting episodes, or long inactive plate boundaries that have been preserved within the crust. Over time, these structures become part of the internal fabric of the plate. Although they may not be visible at the surface, they remain mechanically distinct from surrounding rock. When present-day stresses act across the plate, these inherited weaknesses can be reactivated, producing earthquakes in places that appear, on the surface, to be stable. The stresses that drive intraplate earthquakes are generally transmitted across large distances from active plate boundaries. Even though the strongest deformation occurs at boundaries, the entire plate is subject to forces generated by interactions at its edges. Compression from distant collisions, tension from spreading centers, and a shear from lateral motion can all be distributed through the plate. While these stresses are usually lower in magnitude than those at boundaries, they can still accumulate over long periods. Because intraplate regions often experience fewer small earthquakes, stress may be released less frequently, allowing larger amounts to build before failure occurs. The crust in intraplate regions tends to be older and thicker than at many plate boundaries. It has cooled over long geological time, becoming more rigid and brittle in its upper layers. This rigidity can allow stress to be stored over wider areas. When rupture finally occurs, the earthquake may affect a broad region, even if the total energy released is less than that of the largest boundary earthquakes. The shaking can travel efficiently through the stable crust, sometimes causing effects far from the epicenter. This behavior contrasts with some boundary regions where more fractured and heterogeneous rock can absorb and scatter seismic waves more quickly. Examples of intraplate earthquakes include events in Central and Eastern North America, parts of Australia, and regions within Africa and Asia that lie far from active plate edges. The New Madrid region of the central United States is one of the most studied cases. In the early 19th century, a sequence of strong earthquakes occurred there, far from any major plate boundary. Geological evidence suggests that the region contains an ancient rift system, a zone of weakness formed during a past attempt to split the continent. Although the rift did not develop into a new ocean basin, its structural legacy remains, providing a pathway for stress release. Similarly, parts of Australia experience occasional earthquakes despite being located well within a tectonic plate. The continent's interior contains old fault systems and zones of weakness inherited from ancient geological processes. When stresses transmitted across the Indo-Australian plate act upon these structures, earthquakes can occur. In Africa, areas away from the active East African rift may still experience intraplate seismicity linked to older faults or distant stress fields. These examples show that no part of the crust is entirely isolated from the forces acting across the planet. Intraplate earthquakes also highlight the role of uncertainty in seismic studies. Because they occur less frequently, the historical record is often sparse. This makes it difficult to estimate recurrence intervals or to identify clear patterns over time. A region may appear quiet for centuries and then produce a notable earthquake. Without continuous long-term records, it is challenging to determine whether such events follow any regular cycle or are irregular responses to slowly changing stress conditions. Observations indicate that intraplate seismicity is real and sometimes significant, but it remains uncertain how predictable its timing may be. The distribution of intraplate earthquakes does not form the same clear linear pattern seen at plate boundaries. Instead, it appears scattered, though often aligned with underlying structural features. When plotted on a global map, these events fill in some of the quieter regions between major belts, but they do not dominate the pattern. Their presence adds complexity to the overall picture, showing that earthquake activity is not confined strictly to plate edges. The Earth's crust behaves as a connected system, where forces can be transmitted across large distances and expressed in unexpected places. From the perspective of a possible global pattern, intraplate earthquakes introduce an important caution. If earthquakes are observed in widely separated regions within a similar time frame, Some may occur at active boundaries while others occur within plate interiors. The coincidence of such events can create an impression of widespread global activation. However, each event may arise from different local conditions and stress histories. The presence of intraplate earthquakes means that global seismicity includes both boundary-driven and interior-driven processes, complicating any attempt to identify simple patterns across the planet. At the same time, the study of intraplate earthquakes provides insight into how stress is distributed within plates. It suggests that the forces generated at boundaries do not remain confined to narrow zones, but can influence large areas of the crust. This distributed stress field connects distant parts of a plate, even if it does not produce simultaneous or directly linked earthquakes. The crust behaves as a continuous medium, capable of transmitting forces over great distances, while still responding locally according to its own structure and history. Intraplate regions also demonstrate that apparent stability is relative. A region with few earthquakes over a short observational period may still be capable of significant seismic activity over longer timescales. The absence of frequent small earthquakes does not guarantee safety from larger events. Instead, it reflects the slower release of accumulated stress. This reinforces the importance of long-term geological studies in addition to modern instrumental records when assessing seismic behavior in these areas. At this deeper stage of understanding, the global earthquake pattern becomes more nuanced. It includes not only the well-defined belts at plate boundaries, but also the scattered events within plate interiors. These intraplate earthquakes are less frequent, yet they are part of the same overall system of stress accumulation and release. They remind us that the Earth's crust is interconnected, with forces acting across entire plates and responding through both ancient and active structures. The presence of intraplate seismicity does not negate the dominant role of plate boundaries in shaping the global pattern. Instead, it adds a layer of complexity that must be considered when evaluating whether a pattern is forming across distant regions. Observations indicate that earthquakes can occur both at boundaries and within plates, sometimes within overlapping time windows. It remains uncertain whether such overlaps represent coordinated global behavior or the independent responses of different parts of a dynamic and continuously stressed planet. Below the fractured crust and beneath the surface systems of mountains, trenches, ridges, and continental interiors, one of the most remarkable features of earthquake science comes into view. Some earthquakes do not occur only in the shallow, brittle crust. They also occur far deeper, within slabs of lithosphere that have begun to descend into the mantle. A slab is a large section of cold, rigid outer earth, carried downward where a plate sinks at a subduction zone. As it moves deeper, it does not instantly lose its identity. For long distances and long spans of time, it remains cooler and mechanically stronger than the hotter mantle around it. Because of this contrast, the slab can continue to fracture and deform, producing earthquakes well below the depths typical of most crustal faults. These deep earthquake zones are among the clearest signs that plate tectonics extends far beneath the surface. When earthquake hypercenters are plotted beneath major subduction margins, they often form inclined planes that dip away from the trench and descend into the earth. This pattern reveals the path of the sinking slab. The earthquakes do not fill the mantle uniformly. They trace a narrow to moderate width zone within and around the descending plate, showing that the slab remains a coherent structure as it travels downward. At the surface, a trench and arc may mark the boundary. At depth, the earthquake pattern continues the same system into the interior. The depth range of these events can be divided broadly into shallow, intermediate, and deep earthquakes. Shallow earthquakes occur in the upper tens of kilometers, where ordinary brittle faulting in crustal rocks is common, intermediate earthquakes occur deeper, within the descending slab as it moves beneath the overriding plate and into the upper mantle. Deep earthquakes occur still farther down, in some cases approaching depths of several hundred kilometers. These are extraordinary conditions for seismic rupture, because ordinary rock at such pressure and temperature would be expected to deform more gradually, rather than break in the brittle manner seen near the surface. This is why deep earthquakes have long drawn scientific attention. Their existence is well established by observation, yet the precise mechanism that allows sudden rupture at such depths remains an area of active study. Several processes have been proposed, and some may operate together. One idea is that the cold slab preserves conditions that allow brittle-like failure deeper than would otherwise be possible. Another is that minerals within the slab change structure under increasing pressure, releasing stress and weakening the rock suddenly. A mineral is a naturally occurring solid with a specific crystal structure. As pressure and temperature rise, some minerals transform into denser forms. These transformations may alter the mechanical behavior of the slab and contribute to earthquake generation. Observations indicate that deep earthquakes are associated with descending slabs and with mineral changes at depth. It remains uncertain exactly how these processes combine in every case. The slab itself is under several kinds of stress as it descends. It bends near the trench, where the plate first begins its downward journey. This bending can produce tension in one part of the slab and compression in another. Farther down, the weight of the slab, its resistance to sinking, and its interaction with surrounding mantle material all contribute to internal stress. In some regions, the upper part of the slab may be in tension, pulling apart along its length. In others, compression may dominate as different parts descend at different rates or encounter resistance. Earthquakes within the slab therefore reflect both its inherited structure from the surface and the new stresses imposed by its descent. The geometry of these descending zones differs from one subduction system to another. In some margins, the slab dips steeply into the mantle. In others, it descends more gently for a long distance before steepening. The pattern of earthquake depths follows this geometry. Beneath Japan, Tonga, South America, and other major subduction regions, the inclined seismic zone can be mapped with considerable clarity. This mapping has been one of the strongest tools for understanding the three-dimensional form of plate descent. Even when the slab itself cannot be seen directly, the distribution of earthquakes outlines its path. Deep slab earthquakes are generally not the same as the giant interface earthquakes that occur near the surface, where plates lock together. The largest earthquakes by total rupture area and moment usually occur on the shallow plate boundary. Deep earthquakes can still be large, but their effects at the surface are often different. Because they originate so far below, the shaking may be felt over broad regions. Yet the most intense near-field damage can be less concentrated than in a shallow earthquake of similar magnitude. Still, these deep events matter greatly for understanding the internal behavior of subduction systems, because they show that descent is not a passive process. The slab continues to store and release stress far below the visible boundary. The persistence of slab seismicity also reveals that the lithosphere can remain colder than the surrounding mantle for a long time after subduction begins. Thermal models, seismic imaging, and the earthquake distributions themselves all indicate that temperature contrasts at depth are crucial. A colder slab is stronger and more likely to preserve the conditions needed for sudden failure. As it gradually warms, its ability to generate earthquakes changes. This helps explain why deep seismicity is concentrated in some subduction zones and limited in others. the age of the oceanic plate, the speed of subduction, and the geometry of descent all influence how cold the slab remains and how deep earthquakes can occur within it. Water and hydrated minerals carried down by the slab may also play an important role. Oceanic crust and upper mantle near the seafloor can contain water bound within minerals. As the slab descends and conditions change, some of these minerals become unstable and release water. This process can weaken parts of the slab or surrounding mantle and may contribute to earthquake generation, especially at intermediate depths. The exact details vary by setting, but the general principle is that the descending plate is not chemically or mechanically unchanged as it moves downward. It evolves, and that evolution affects seismic behavior. When considering a possible global earthquake pattern, descending slabs introduce an inner layer that is not visible from the surface alone. Two distant subduction zones may each host deep earthquakes within their sinking plates during the same broad period. To a surface observer, this may appear as another sign of broad planetary coordination, yet each deep event is rooted in the internal condition of a specific slab, including its temperature, mineral state, geometry, and stress history. Observations confirm that deep and intermediate earthquakes are strongly tied to subduction and slab properties. It remains uncertain whether the timing of such earthquakes in widely separated slabs reflects any strong global synchronization beyond the fact that many subduction systems are active at once. At this depth, the meaning of an earthquake pattern changes. The event is no longer only a rupture in the upper crust or along a surface boundary. It becomes part of a descending structure carried into the mantle, still cold enough, stressed enough, and coherent enough to fail. The global map of earthquakes extends downward into inclined planes beneath arcs and coasts, following the hidden path of plates returning to the interior. These descending slabs are among the clearest signs that the restless outer shell remains connected to deeper earth, and that the story of earthquakes continues well below the ground that people feel beneath their feet. Beneath the descending slabs and the fractured crust lies the broader mantle, a vast region of solid rock that behaves differently depending on depth, temperature, and time. Although it is solid, the mantle can flow slowly over geological timescales, allowing heat from the interior of the Earth to move outward. This slow movement is often described as convection, where warmer material rises and cooler material sinks. The motion is not fast or turbulent in the way that fluids move at the surface. It is gradual, measured in centimeters per year, yet over millions of years it shapes the structure and motion of the plates above. The mantle is not uniform. It contains variations in temperature, density, and composition. Some regions are slightly hotter and less dense, tending to rise. Others are cooler and denser, tending to sink. These differences create broad patterns of circulation that extend through large volumes of the interior. While the details of this circulation are still being studied, its general presence is well supported by seismic imaging and by the distribution of surface tectonic features. The plates at the surface are coupled to this deeper system. Their movement reflects, in part, the forces generated by mantle flow and by the sinking of cold slabs. Stress within the mantle does not usually produce earthquakes in the same way as in the brittle crust. At greater depths, higher temperatures allow rock to deform more smoothly, without sudden fracture. This process is called ductile deformation, meaning that the material can bend and flow rather than break. Because of this, most of the mantle is not seismically active in the sense of producing ordinary earthquakes. Instead, it transmits stress gradually, redistributing forces over large distances. The mantle acts as both a driver of plate motion and a medium through which stress can be transferred. even if it does not release that stress in frequent seismic events. The interaction between mantle flow and plate motion influences where stress accumulates in the crust and along plate boundaries. For example, where a cold slab sinks into the mantle, it can pull the rest of the plate along, a process sometimes called slab pull. This force can increase stress at distant parts of the plate boundary. Similarly, upwelling regions, where hotter material rises, can contribute to the separation of plates at divergent boundaries. These deep processes do not act in isolation. They are part of a connected system in which surface motion and interior flow influence one another. Because the mantle connects large regions of the Earth, it raises the possibility that stress changes in one area could, in principle, influence distant regions over time. However, this influence is generally slow and diffuse. The timescales of mantle flow are long compared with the sudden release of energy in an earthquake. While the mantle sets the long-term conditions for plate motion and stress accumulation, it does not usually transmit rapid, short-term signals that would synchronize earthquakes across the globe. Observations indicate that mantle processes shape the overall distribution of tectonic activity. It remains uncertain whether they contribute to short-term clustering of earthquakes in distant regions. Seismic waves generated by earthquakes provide one of the main tools for studying the mantle. As these waves travel through the Earth, they change speed and direction depending on the properties of the material they pass through. By analyzing these changes, scientists can infer variations in temperature and composition within the mantle. This technique has revealed large-scale structures such as subducted slabs extending deep into the interior and broad regions of upwelling material. These structures show that the mantle is not a simple uniform layer, but a dynamic environment with complex patterns of motion. The presence of these structures also affects how stress is distributed within the Earth. A sinking slab can alter the flow of surrounding mantle material, creating regions of compression and extension at depth. Over long periods, these changes can influence the stress state of the overlying plate. However, the connection between deep mantle processes and individual earthquakes at the surface is indirect. The mantle sets the stage, but the immediate cause of an earthquake remains the failure of rock along a fault in the crust or within a slab. Temperature plays a crucial role in determining how the mantle behaves. Hotter regions are more likely to deform smoothly, while cooler regions can retain more rigidity. This contrast helps explain why subducting slabs, which are cooler than the surrounding mantle, can continue to produce earthquakes at depth. It also explains why most of the mantle does not generate earthquakes, even though it is under stress. The balance between temperature, pressure, and composition controls whether rock will flow or fracture. Another factor is the presence of chemical variations within the mantle. Different minerals have different properties, and changes in mineral structure can affect how stress is stored and released. At certain depths, pressure can cause minerals to transform into denser forms, altering the physical behavior of the rock. These transformations can influence the dynamics of mantle flow and the behavior of descending slabs. While these processes are important for understanding the deep Earth, their direct role in producing surface earthquake patterns remains an area of ongoing research. When considering a possible global pattern of earthquakes, the mantle introduces a deeper level of complexity. It connects distant regions through slow circulation and shared physical conditions. Yet it does not operate on the same timescale as seismic events. Two distant earthquakes may occur within days or months of each other, but the mantle processes that influence their stress environment act over much longer periods. This difference in timescale makes it difficult to attribute short-term global patterns directly to mantle dynamics. Observations indicate that the mantle plays a fundamental role in driving plate motion and shaping the long-term distribution of stress across the Earth. It remains uncertain whether variations in mantle flow can produce short-term synchronization of earthquakes in widely separated regions. The evidence suggests that while the mantle influences the conditions under which earthquakes occur, it does not provide a simple mechanism for linking events across opposite sides of the planet in a direct and immediate way. At this depth, the understanding of earthquakes becomes more connected to the broader system of the Earth's interior. The mantle is not a source of frequent seismic rupture, but it is the engine that moves the plates and redistributes stress over vast distances and long times. The global pattern of earthquakes, seen at the surface and within descending slabs, rests upon this deeper foundation of slow, persistent motion. The connection between surface events and deep processes is real, but it unfolds over timescales that are far longer than the sudden moments in which the ground begins to shake. When an earthquake begins, the rupture may be local, rooted in one fault or one portion of a descending slab, but the motion it releases does not remain local. It sends waves through the Earth in all directions, moving outward through rock, crossing boundaries between layers, bending, reflecting, weakening, and in some cases returning after travelling immense distances. These waves are the reason a single earthquake can be detected by instruments around the globe. They are also one of the main reasons that the idea of a planetary earthquake pattern feels so vivid. A major rupture in one region does not stay hidden there. Its motion enters the whole body of the Earth. Seismic waves are vibrations that carry energy through solid ground. Some push and pull material in the same direction that the wave travels. Others move material side to side or up and down as the wave passes. The first type, often called compressional motion, usually travels faster. The second type, often called shear motion, is slower and cannot move through liquid in the same way. At the surface, additional kinds of waves can travel along the outer layers, often producing strong shaking during damaging earthquakes. These wave types differ in speed and behavior, but together they form the expanding pulse that carries the earthquake beyond its origin. As the waves move through the crust and mantle, they encounter regions of different density, temperature, rigidity, and composition. Each contrast changes the wave path. Some waves are refracted, meaning they bend as they pass into material where their speed changes. Some are reflected back. Some are scattered by rough structures, broken crust, or complex fault zones. Some lose strength gradually as energy is absorbed and redistributed. Even so, large earthquakes produce signals strong enough to cross the full diameter of the Earth. Seismometers far from the rupture record their arrival minutes later, then later arrivals from waves that have taken longer paths through the deep interior. This global travel of seismic energy has immense scientific value. It reveals the structure of the planet because wave speed depends on the material crossed. It shows where the mantle is colder or warmer, where slabs descend, where the outer core is liquid, and where internal boundaries lie. Yet the waves also raise another question. If earthquake energy can cross the Earth so quickly, can it influence faults far away? Can one earthquake, through its waves, disturb another fault on the far side of the world strongly enough to help trigger another rupture? Observations indicate that dynamic triggering can occur. Dynamic triggering means that the passing waves from one earthquake can alter stress temporarily on distant faults, and, in some cases, coincide with small earthquakes, fluid movement, volcanic unrest, or tremor in remote regions. Tremor is a weak, prolonged seismic signal that differs from an ordinary earthquake and may reflect slow or distributed motion. This effect is real and has been observed after some major earthquakes. It shows that the Earth does not merely record a wave in silence. In some settings, distant faults and fracture system respond to the passing disturbance. Even so, the existence of dynamic triggering does not automatically imply a strong global pattern of major earthquakes. The stress change from passing waves is usually temporary and often modest, compared with the long, accumulated tectonic stress already present on a fault. A distant fault must already be close to failure for the passing waves to make a decisive difference. In many places, the waves pass with no clear lasting consequence. In others, they may trigger small events but not large ruptures. This means that wave transmission provides a plausible pathway for influence across great distance, but not a simple explanation for repeated opposite side pairing of large earthquakes. There is also static stress transfer, which is different from dynamic triggering. Static stress change refers to the permanent redistribution of stress around a fault after it ruptures. This effect is well documented near the source region, where nearby faults may be brought closer to failure or pushed farther from it. However, static stress change decreases rapidly with distance. Across global scales, especially across opposite sides of the Earth, it becomes extremely small compared with the local tectonic loading. For that reason, static transfer is not usually considered a strong mechanism for linking far separated large earthquakes. Seismic waves, by contrast, truly do circle the globe. After a very large earthquake, some waves travel around the Earth more than once. Instruments can detect repeated arrivals as the energy follows long paths along the surface or through the interior. Near the antipode, where the opposite point lies, wave energy may sometimes be focused by the geometry of the sphere and the internal structure of the Earth. This has long attracted attention because it gives the antipodal region a physical significance beyond simple map symmetry. Yet wave focusing does not guarantee fault rupture there. It means only that the incoming motion may be altered in a way that concentrates some energy. Whether this matters for earthquake triggering depends on the local condition of faults already present in that region. The idea of opposite sides of the Earth therefore gains a real but limited physical basis in wave propagation. A major earthquake launches motion that the whole planet feels instrumentally. The antipodal region is not merely a geometric opposite. It is also a place where some seismic phases may converge after travelling through the Earth. However, the leap from detectable motion to triggered major earthquake is large. The distant fault must have its own stress history, its own frictional state, its own fluids, and its own structural weaknesses. A wave can disturb that system, but it cannot replace the long preparation that tectonic loading requires. Studies of distant triggering show mixed outcomes. Some major earthquakes are followed by increases in small seismicity or tremor at remote sites. Others are not. Some regions appear more sensitive than others, especially where fluids are important or where faults are already weak and near failure. In contrast, clear repeated examples of one major earthquake reliably causing another major earthquake on the far side of the world remain difficult to establish. The data suggest possibility. Not regularity, they suggest influence, not certainty. This distinction matters when clusters of large earthquakes occur in distant regions within months or years. It can be tempting to imagine the first rupture sending a signal through the planet that sets off the next, and then the next. In some individual cases, such an influence cannot be ruled out entirely. Yet the Earth always contains many stressed faults near active boundaries. Some will fail in any case, with or without a remote passing wave. The challenge is to determine whether the timing departs clearly from what chance and independent tectonic loading would already produce. That standard is difficult to meet, especially for rare great earthquakes. Observations indicate that seismic waves from large earthquakes travel through the entire Earth, can be recorded worldwide, and can in some circumstances trigger small distant seismic responses. It remains uncertain how often this process contributes meaningfully to the timing of large remote earthquakes, especially across opposite sides of the planet. The physical pathway exists, but its practical influence appears limited and highly dependent on local conditions. At this stage of the inward path, the Earth appears not as separate seismic provinces acting in complete isolation, but as a connected solid body that carries motion from one rupture through its whole interior. Earthquake waves cross oceans, continents, mantle layers, and the deep coreward paths of the globe. They reveal the hidden structure of the planet and occasionally disturb distant faults, yet they do not erase the importance of place. Even when the whole Earth rings with a passage of seismic energy, each later earthquake must still begin within its own faulted rock, under its own stored stress, at the point where local resistance finally fails. To determine whether a global earthquake pattern is forming, especially one that appears to link distant or opposite regions of the Earth, observation alone is not enough. The Earth is always active at some level, and clusters of earthquakes can arise naturally within a system that contains many stressed faults. To move beyond impression, scientists rely on instruments, measurements, and statistical analysis. These tools allow the comparison of observed earthquake sequences with what would be expected from a system operating without global coordination. Only through such careful testing can a possible pattern be distinguished from coincidence. The foundation of modern earthquake detection is the global network of seismometers. These instruments are designed to detect ground motion with high sensitivity, recording vibrations that are far too small to be felt by people. They are distributed across continents, islands, and oceanic regions, forming a system capable of locating earthquakes anywhere on the planet. When an earthquake occurs, its seismic waves arrive at different stations at slightly different times. By comparing these arrival times, scientists can determine the location and depth of the event, as well as estimate its magnitude, a measure of the energy released. Over time, these observations are compiled into global catalogues. Each entry includes the time of occurrence, the location, the depth, and the magnitude of an earthquake. With thousands of events recorded each year, these catalogues provide a detailed record of seismic activity. They allow researchers to examine patterns over a wide range of timescales, from seconds to decades. When investigating a possible global pattern, scientists often focus on larger earthquakes, because they are less numerous and more likely to stand out against the background of constant small seismic activity. One method used to test for patterns is statistical comparison. Scientists begin with a model of random occurrence, where earthquakes happen independently at a given average rate. They then compare the actual sequence of events with this model. If the observed clustering in time or space significantly exceeds what would be expected by chance, it may indicate that additional processes are at work. However, because large earthquakes are rare, the number of events available for analysis is limited. This makes it difficult to reach strong conclusions, especially over short observational periods. Another important tool is satellite geodesy, which measures the movement of the Earth's surface with high precision. By tracking the position of points on the ground over time, scientists can detect slow deformation caused by plate motion and stress accumulation. This information helps identify regions where strain is building and where future earthquakes may be more likely. While geodesy does not predict the exact timing of an earthquake, it provides a continuous measure of the underlying processes that lead to rupture. When combined with seismic records, It offers a more complete picture of how stress evolves across the planet. Researchers also examine correlations between earthquakes in different regions. They look for repeated instances where large events in one area are followed by events in another area within a defined time window. If such correlations occur more often than expected by chance, they may suggest a connection. However, establishing this requires careful definition of both spatial and temporal criteria. If the criteria are too broad, apparent correlations may arise simply because earthquakes are common in certain active zones. If the criteria are too narrow, real connections may be missed. The balance between sensitivity and specificity is a central challenge in this analysis. The concept of antipodal or opposite side relations can also be tested directly. For each significant earthquake, scientists can calculate the antipodal region and examine whether seismic activity there increases within a certain time frame. This approach has been applied in various studies. Some results suggest minor increases in seismic response at antipodal distances, often involving small earthquakes or tremor. Other analyses find no consistent pattern for large earthquakes. Observations indicate that while antipodal effects may occur in limited ways, they do not form a strong or regular global pattern of major seismic events. In addition to statistical methods, physical modeling plays a role. Scientists simulate how stress changes propagate through the Earth, how seismic waves interact with distant faults, and how different boundary conditions affect earthquake timing. These models incorporate knowledge of rock mechanics, plate motion, and mantle dynamics. They help test whether proposed mechanisms for global interaction are plausible under realistic conditions. So far, such models generally support the idea that local conditions dominate earthquake occurrence, while global interactions are secondary and often weak. The quality of data also matters. Modern seismic networks provide detailed records for recent decades, but earlier records are less complete. Historical accounts may describe large earthquakes, but smaller events are often missing. This uneven data coverage can influence the detection of patterns. A cluster of large earthquakes in recent years may appear unusual simply because it is observed with greater detail than similar clusters in the past. To address this, scientists use long-term geological evidence, such as fault scarps and sediment records, to extend the history of seismic activity beyond the instrumental era. Uncertainty is an inherent part of this work. The Earth's seismic system is complex with many interacting variables. Even with advanced tools, it is difficult to isolate the influence of one factor from another. When a possible pattern is identified, it must be tested against multiple hypotheses, including the possibility of random occurrence. Observations indicate that while regional clustering and aftershock sequences are well understood, evidence for strong global synchronization of large earthquakes remains limited. It remains uncertain whether any observed alignment of distant events represents a persistent pattern or a temporary coincidence within a dynamic system. Communication of these findings is also important. Reports of multiple large earthquakes within a short period can lead to public concern about a global trend. Scientific analysis provides context, showing whether such sequences fall within expected variability. While it's natural to look for meaning in striking events, careful measurement and comparison are needed to avoid drawing conclusions that are not supported by evidence. The goal is not to dismiss patterns, but to evaluate them rigorously using all available data. At this stage of the inward path, the study of earthquakes becomes a matter of measurement, comparison, and cautious interpretation. The instruments record the motion, the catalogues preserve the history, and the analyses test the significance of observed sequences. A possible global pattern must pass through this process before it can be accepted. The Earth may present moments where distant regions appear to act in concert, but only through detailed examination can it be determined whether such moments reflect a deeper connection or the natural variability of a constantly active planet. At the innermost stage of this inquiry, the broad map of earthquakes, the geometry of opposite points, the timing of clustered events, the motion of plates, the fractured crust, the sinking slabs, the slow mantle, and the travelling waves all come together in a single careful question. What is actually known about a possible global earthquake pattern, especially one that seems to form across opposite sides of the Earth, and what remains uncertain? By this point, the answer is neither dramatic nor empty. It is structured, measured, and incomplete in the ordinary scientific sense. The Earth does show strong global organization in where earthquakes occur. It does show intervals in which widely separated regions are active within similar spans of time. It does allow seismic waves to travel through the whole planet and sometimes disturb distant faults. But these truths do not automatically combine into proof of a recurring, planet-wide, opposite-side pattern of major earthquakes. The strongest conclusion is spatial. Earthquakes are not randomly scattered across the surface of the Earth. They concentrate along tectonic plate boundaries, especially subduction zones, major transform faults, spreading centers, and some continental collision belts. Additional earthquakes occur within plate interiors, often along ancient zones of weakness. This distribution is one of the clearest and most durable findings in Earth science. It has been confirmed by instrumental records, field studies, seafloor mapping, geodesy, and the theory of plate tectonics. In this sense, there is unquestionably a global earthquake pattern. It is the pattern of a segmented outer shell whose moving plates store and release stress unevenly. The next conclusion is temporal, and it is more limited. Earthquakes do cluster in time at regional scales. Aftershock sequences are real. Stress changes near a major rupture can affect nearby faults. Some periods contain several large earthquakes around the world, while others contain fewer. This means that the global record is not perfectly uniform through time. Yet the existence of temporal variation does not by itself establish a strong organizing process linking distant major earthquakes. Rare events naturally appear clumped in some intervals and sparse in others, even in partly random systems. Statistical studies have often found that apparent global clustering of the largest earthquakes becomes less persuasive when aftershock sequences and expected variability are taken into account. Observations indicate some fluctuation in the global rate of large earthquakes. It remains uncertain whether that fluctuation reflects a persistent planet-wide forcing mechanism. The specific idea of opposite-side pairing becomes weaker when tested strictly. True antipodes are exact geometric opposites on the sphere, and many major seismic belts do not face one another in neat antipodal arrangements. Often the point opposite an active margin lies in a relatively quiet oceanic region. Flat maps can exaggerate visual impressions of symmetry. Once positions are calculated on the globe itself, many apparent opposite-side relationships turn out to be only broad separations rather than true antipodal matches. This does not make them meaningless, but it changes the claim. A broad far-side correspondence is easier to observe than a strict antipodal one, and also easier to obtain by chance in a planet with multiple active belts. The question of physical linkage across great distance also has a measured answer. Large earthquakes send seismic waves through the whole Earth. These waves can be recorded globally and can, in some circumstances, dynamically trigger small distant events, tremor, or localized responses in systems already close to failure. This is a real physical effect. Yet it is not the same as establishing a robust tendency for one great earthquake to trigger another great earthquake on the far side of the planet. For that stronger claim, the evidence remains limited. Dynamic triggering is often transient and selective. Static stress transfer, which is important near the source, becomes very small over global distances. Mantle processes, meanwhile, act over long time scales and do not provide a simple short-term synchronization mechanism for distant earthquakes. Observations indicate that influence across large distance is physically possible in limited ways. It remains uncertain how often that influence meaningfully changes the timing of major remote ruptures. Another firm conclusion concerns local control. Every earthquake, however global the pattern may appear, still begins in a particular faulted region with its own stress history, frictional state, fluids, temperature, geometry, and structural inheritance. A distant wave, a broad tectonic setting, or a global period of elevated activity cannot produce a major earthquake unless the local fault system is already capable of failure. This means that local readiness remains central. The Earth may be connected as a solid body, but it does not respond everywhere in the same way. The same passing disturbance may leave one region unchanged, trigger small earthquakes in another, and coincide with a major rupture in a third only because that third fault was already near failure. There is also an important difference between recognizing pattern and inferring cause. Scientists often begin by noticing recurring shapes in data. A series of large earthquakes in distant arcs or mountain belts may genuinely look suggestive. But pattern recognition is only the first step. It must be followed by geometric testing, temporal comparison, statistical evaluation, and physical modeling. Many apparent global alignments weaken under this scrutiny. Some limited relationships survive. Regional stress transfer is well supported. Deep slab seismicity follows clear physical structures. Dynamic triggering at distance is credible in selected cases. Strong repeated opposite side pairing of major earthquakes, however, remains difficult to demonstrate with confidence. This careful position is not a sign of ignorance in the broad sense. It is the normal boundary between well-supported structure and unresolved detail. Scientists know a great deal about why earthquakes happen, where they are most likely, and how their waves move through the planet. They know that subduction zones produce the largest events, that ridges and rifts produce shallow extensional earthquakes, that old continental faults can reactivate, that descending slabs remain seismically active at depth, and that the mantle drives plate motion over long spans. They also know that the timing of individual large earthquakes remains difficult to forecast, and that the interpretation of global clustering depends strongly on sample size, method, and definition. So the deepest conclusion settles into a calm and restrained form. Earth does possess a global earthquake pattern, but it is primarily the long-standing tectonic pattern of moving plates, active boundaries, inherited faults, and uneven stress release. Earth does at times display striking sequences of distant earthquakes within limited intervals. Earth does transmit motion from one rupture through its whole interior. Yet current evidence does not support a simple picture in which the planet regularly develops a strong, clear, opposite side pattern of major earthquakes in a way that can be confidently separated from coincidence, local readiness, and the background behavior of many active tectonic systems. Observations indicate connection, structure, and occasional remote influence. It remains uncertain whether these amount to a recurring, predictive, globe-spanning seismic pattern of the kind the eye is inclined to imagine when several distant earthquakes happen close together in time. In that uncertainty, the subject comes to rest without becoming vague. The Earth is active, organized, and deeply interconnected, but not neatly symmetrical. Its outer shell breaks where plates converge, part, and slide. Its slabs descend while still carrying stress into the interior. Its waves ring through the globe after every major rupture. Its faults wait in different states of readiness. What appears, from one brief human interval, to be a forming global pattern may sometimes be meaningful, sometimes coincidental, and often both in part because real structure and random timing coexist in the same restless planet. The scientific view remains patient. It accepts the global map, tests the apparent sequence, and separates what can be measured from what can only be suspected. In that slow and careful separation, the Earth keeps its complexity, and the pattern remains real in some ways, limited in others, and unfinished in all the ways that still invite quiet study. The planet grows quiet again in the mind when the details are allowed to settle into their proper scale. The surface is not still, yet neither is it governed by simple balance from one side to the other. Earth carries long belts of strain around ocean margins, through mountain systems, across ridges on the seafloor, and within old scars left inside continents. Some faults break often, some wait for long spans, some answer to nearby changes, others remain silent until their own threshold is reached. Across all of them, the deeper motion of the planet continues without haste. Beneath the landscapes of coast, island, plateau, basin, and plain, the plates move by very small amounts each year. Rock bends where it can, locks where it must, and sometimes slips in a moment that is brief compared with the long preparation before it. Waves then pass through the whole Earth, and instruments far away record the motion. In that sense, every large earthquake becomes global for a time, not because the whole planet breaks at once, but because the whole planet carries the signal. The idea of opposite sides remains meaningful as geometry and as a reminder of Earth's wholeness. Yet the stronger image of paired planetary unrest remains uncertain. The world does not divide into perfect mirrors. It holds asymmetry, inheritance, roughness, and chance together with real physical structure. That mixture is what makes the subject difficult, and also what makes it clear enough to study with patience. So the final image is not one of a world suddenly falling into hidden order, nor of a world without order at all. It is a world whose crust releases strain unevenly, whose deeper interior sustains the slow engine of motion, and whose earthquakes reveal connection without simple symmetry. The ground rests, then adjusts, then rests again, always within a larger rhythm too slow for ordinary notice, but steady enough to shape the face of the Earth.